Problem number 37. There are some pictures going on, so I printed off some pictures so we can see them nice and big. Part A, we're given two vector fields here, formulas, and three pictures. We have to match them up. So how might we go about doing? Let's do some test points. In the previous take of this video, I started to figure out f of 0.5 and 0.5 and g of 0.5, 0.5. That would be the middle right here. F of 0.5, 0.5 would be negative 0.5, positive 0.5. Negative 0.5 in x slot means we're pointing to the left. Positive 0.5 means that we're pointing up. So to the left and up. This is to the right and up. This is to the right and up. This one is our only choice for f. For g of 0.5, 0.5 is 0.25 and 1. Okay, so it's pointing to the right and up. Both of those are pointing to the right and up, but it's pointing very slightly to the right and more up. And I think that describes this better than this. So that is G. Okay, that is part A. For part B, again, I make this picture a little bit bigger here. Exactly one of these vector fields below is not conservative. Which one? And so the little fact I'm going to use here to figure out which one is not conservative is that we're going to use the path independence property, which says that integral along a curve C1 has equal to integral along a curve C2 of f in each case if C1 and C2 share the start and end. So what we're going to do is that we're going to pick one of these, the one that's not conservative, and I'm going to pick two paths in there, and we're going to see that with the two paths, they'll start at the same point, end at the same point, but the line integrals will be different. And so that will be enough to show it's not path independent. And so the one that turns out to be not path independent, which just means not conservative, is this one right here. Let's take this as point P and this as point Q. And I'm going to draw the following two paths in it. So this will be curve C1. And this will be curve C2. So if this were a conservative vector field, these two line integrals would have to give you the same thing. But along C1, okay, on this stretch it's 0. On this stretch it will be something positive. For C, so the overall answer will be positive. On this stretch it will be something positive. On this stretch, it will also be something positive. And I feel pretty confident in saying that the line integral of f from here to here equals the line integral of f from here to here. Just, those arrows look about the same, just shifted up here. But, so those two should be about the same, but this is positive and that's 0. So I think this convinces me that the line integral of f along C2 is bigger than the line integral of f along C1. Because those are different, I can conclude that's not conservative. Okay, that is part B. For part C, we have this picture. I didn't blow up because it's big enough. Choose the form for R of t that gives a streamline for the vector field shown here. So what's a streamline? Think of this as giving water flow or something like this. Drop a leaf in, like let's say right here. How will it go? The leaf will curve like that, something like that. Okay, which one of these formulas, parametric formulas, gives a graph that looks something like this? D is out. D is 1/2 comma t. X is always 1/2. That would just be a straight line going up. No. X is t over 2, y is t. This is actually going to be an equation of a straight line as well. We can tell this is not, there aren't going to be straight lines. Streamlines, no. So these two are going to give parabolas. So these are our two choices here. For choice C, like x is t, y is t squared over 2, that would be like y is x squared over 2. This one would be y is t, x is equal to y squared over 2. So for y is x squared over 2, that parabola is going to look like this, and in the first quadrant, just that much of it. That doesn't match our picture, has the wrong concavity, but this one, this will look more like that, so choice B there. Okay, part D. Suppose E is a vector field R2 where the streamline through 1, 0 is this ellipse. Is E conservative? The answer is no. Why is that? The only thing that matters is the fact that this is a closed loop. This is the streamline here is a closed loop. We end where we begin. And so the way that we come up with a streamline is that we're following the vector field at all points along the streamline. So as we go around this ellipse, the circulation, the line integral around here is very positive because at each point here, the dot product is going to be very positive. So we're adding up lots of positive things here. And so we conclude that the integral around this curve C of f dot dr, this is positive, but it needs to be 0 if E were to be conservative. So that's part D. Okay, let's move on and do problem 38. So also another picture problem. Let's see, where did I stick the picture for that? It is right here. Okay, sorry for the delay. Yeah, so these are, let me readjust this. This is the 3 pictures that we have going on in problem 38. So we're asked different questions, which one's conservative, which one has this formula, stuff like that. I'm going to do it a little bit out of order just so that the picture doesn't get too marked up. For the first one, which vector field has formula y minus 1 comma y? Well, we could just do test points here. For example, at the origin, this vector would be minus 1, 0. So straight to the left. This isn't straight to the left. That is straight to the left. This isn't straight to the left. And so I think pretty confident that we can say G is this vector field. Also, another way to see this is that this formula here only depends on y, doesn't depend on x. And we can see here in G that the vector field is constant along fixed values of y as x varies. So that goes along with it. So part B, the answer here is G. For part C, the divergence of H is constant. We see stuff is expanding from the middle here. We see stuff is expanding here. The value of the divergence of H is positive here. If you don't want to just look and say that this is expanding, a not bad guess for the formula for H might be something like H is equal to x comma y. And if you do the divergence of x comma y, the x partial derivative of this is 1, the y partial derivative of y is 1. Okay, 1 plus 1 is 2. Okay, for D, the vector field curl F is constant. What's the value of curl F here? It's not 0, 0, 0 because we clearly see that there's rotation going on here. So is it pointing into the page? That would be 0, 0, minus 1, that direction. Or it would be pointing out of the page, 0, 0, positive 1. Right hand rule, I've got my right hand here. I curl my fingers in the direction of the rotation. This direction, my thumb is pointing up at the camera. So that would be 0, 0, positive 1 there. in the positive k-hat direction. Okay, so which vector field is conservative? I skipped that one earlier. Let me go back to it. This is a conservative vector field. And the idea is that if we do a vector line integral around any closed loop here of f, and we find a circulation around any closed loop here, we'll get 0. So we can just if I just kind of draw this circle here, and I just kind of draw this circle here, then we can see that it's going to be perpendicular to all of the vectors, so it'll just be uniformly 0 all the way around. I mean, but just showing one example isn't enough to really convince us that this is conservative. So let me convince you that these two are not conservative. So for f, let me just draw this circle right here. If this is curve C, integral around curve C, the circulation of f dot dr around curve C is going to be very positive. You know, at basically every point along my curve, the dot product between the direction vector of the curve and the vector field f is going to be positive. So, you know, right there, you know, that vector and the direction vector, it's a positive dot product. Right here, that there's a direction vector, there's the vector field positive dot product there, and there positive dot product. So that shows us that this will be positive. It's not 0. F ain't conservative. For G, what I'm going to do is that I'm going to do it more similarly to what we did in problem 37 and show that this is not path independent. So let me pick this point here as P and this point here as Q. And if we go along this curve C1, this is very big. You know, we are picking up a very large value going from here to here because we're going in the same exact direction as those vectors, and it's still going to be positive here. Whereas instead, if we went here and here, well, along this side, we're moving perpendicular to the vector field, so that will just be 0. This will be positive. It's similar value to over here, but I think we can see that the integral along C1 will be bigger than the integral along C2. This isn't conservative. So that shows us H is conservative. For part B, we're asked, let C be this circle with the formula, it's a circle of radius a half centered at the point 1/2, 1/2. Is the 2D flux integral over C of H dot N ds, is this positive, negative, or 0? And so flux is basically your taking dot products of the vector field with the normal vectors to our curve. So this answer is going to be positive. Let me give you two reasons why this is positive. So in some places, the dot product of a normal vector with the vector field is positive, like right there. And in other places, you know, the dot product of the normal vector of the vector field is negative, like right there. But the point is that the vector field is greater in magnitude on this side where it's positive, and on this side where it's negative. So there's more of a positive contribution than a negative contribution. That shows us that this is positive. We can also use the flux divergence form of Green's theorem here. So the flux divergence form of Green's theorem will say the flux of H over this closed curve C is equal to the double integral over the region inside here of the divergence of H. But we just said the divergence of H is always positive. It's some positive constant here. You know, that was part C. And so that, if we're always integrating something that's always positive, well, this integral is going to be positive. That's another way to get there.